The pyramids of Giza stand as one of history's greatest enigmas. For centuries, we believed we understood their construction, a story of ramps and immense manpower. That long-held story is now crumbling. A radical new theory is dismantling the foundations of traditional Egyptology, and it has experts completely baffled. By the end of this, you will understand a revolutionary idea that could force us to rewrite ancient history. We will explore the chemical secrets hidden within the stone itself and confront a startling possibility that redefines ancient ingenuity. What does true innovation look like when it comes from the distant past for generations? The story of the pyramids has been told the same way. This is the standard narrative, the one you likely learned in school and have seen depicted in countless documentaries. It is a tale of monumental human effort, a project so vast it staggers the modern mind. According to this classic view, the Great Pyramid was built by a massive workforce of conscripted laborers, not slaves as once thought, but farmers who worked during the annual flooding of the Nile when their fields were underwater. Their tools were simple, primarily copper chisels and stone hammers, materials that seem almost laughably soft against the hard limestone and granite they were meant to shape. The central pillar of this entire theory is the ramp. Enormous earthen ramps, built taller and longer as the pyramid grew, are proposed as the only way to haul blocks weighing multiple tons into place. We are shown animated reconstructions of these ramps winding their way up the structure's sides, with thousands of workers straining on ropes, dragging sledges loaded with stone. The sheer scale of the logistics is presented as the true marvel, a testament to the organizational power of the pharaoh's administration. This story is clean, logical, and paints a picture of ancient ingenuity that we can easily understand. It fits neatly into our historical framework, but what if this compelling narrative, the one we have accepted for so long, is built on a foundation that is beginning to crack? Yet that foundation of ramps and ropes begins to crumble under the weight of the stones themselves. Consider the sheer mass of the granite blocks used in the pyramid's inner chambers. Some of these behemoths weigh more than 70 tons, a mass equivalent to a fully loaded semi-truck. Now picture hauling that semi-truck up a steep, unstable earthen ramp, using only ropes, wooden sledges, and human muscle. The physics alone become a nightmare. The ramp would need to be impossibly wide and long to maintain a gentle enough slope, and the pressure on the fragile stone edges of the structure below would have been catastrophic. Where is the evidence for such colossal earthworks? Archaeologists have searched for decades, yet no trace of these enormous ramps has ever been found. Not a single definitive ramp structure, no vast deposits of construction debris, nothing. The very mechanism that is central to the traditional story is completely missing from the archaeological record. Then there is the matter of precision. The stones of the Great Pyramid are not merely stacked, they are cut and fitted together with gaps of less than 1/50th of an inch, a tolerance rivaling modern engineering. The surfaces are often perfectly flat, and the corners are sharp and true. How was this achieved with simple copper tools, a metal softer than the granite it was supposedly used to shape? It would be like trying to carve a diamond with a butter knife. These are not the rough, uneven surfaces you would expect from a massive, rushed construction project. They are the hallmarks of a technology we do not yet understand, a level of craftsmanship that defies our accepted timeline of human innovation. The old story, for all its comfort, is filled with holes too large to ignore. This is where the narrative fractures completely, revealing a possibility so radical it redefines ingenuity. The new theory proposes something almost alchemical, a lost knowledge that transforms our understanding of the pyramid's very substance. It suggests that the ancient builders did not simply cut and haul every single block. Instead, they mastered a form of advanced chemistry, creating a type of synthetic stone. Imagine a kind of ancient concrete, a liquid stone that could be poured into molds, setting into a material indistinguishable from natural rock. This is the geopolymer hypothesis, a terrestrial yet revolutionary idea that turns the story of brute force into one of profound chemical intelligence. The central premise is startlingly simple, yet its implications are earth-shattering. What if the pyramid's immense limestone blocks were not all dragged from distant quarries, but were cast directly in place, layer by layer, like a colossal, slow-setting sculpture? This would eliminate the need for the impossible ramps and explain the mind-boggling precision of the joints. The stones fit together so perfectly not because they were carved with impossible accuracy, but because they were formed that way, fusing together as they hardened. This is not about extraterrestrial intervention. It is about a forgotten chapter in human science, a sophisticated application of geopolymer chemistry that was lost to time. The theory posits that the Egyptians developed a recipe, a slurry of locally available limestone, a specific clay rich in kaolinite, and a reactive salt like natron from the dry lake beds. Mixed with water, this concoction would start a chemical reaction, creating a cement-like paste that could be tamped into wooden formwork. This material would not just dry, it would undergo a geosynthesis, a molecular reorganization that creates a new, incredibly hard stone. The result is a block that is chemically and physically identical to natural limestone, but cast to a perfect shape. It explains the lack of tool marks, the absence of quarrying evidence for millions of blocks, and the supernatural flatness of the surfaces. The pyramid, under this new light, is not just a pile of rocks. It is the world's most enduring chemical experiment, a monument not only to a pharaoh's power but to a civilization's lost scientific genius. The stones themselves are now beginning to speak, revealing secrets locked inside for millennia. Under a microscope, samples from the Great Pyramid's casing stones tell a story that defies conventional quarrying. Researchers have identified tiny, spherical air bubbles trapped within the stone's matrix. These are not features you find in solid limestone formed over eons under immense pressure. These bubbles are the classic fingerprint of a poured liquid, a slurry that trapped air as it was mixed and poured into place, much like you would see in modern concrete. It is a microscopic anomaly with monumental implications. Further analysis has uncovered strands of organic material like hair or plant fibers embedded deep within the block. In a natural quarry, a block would be carved from a massive deposit, its interior pristine. But if you are mixing a thick, cement-like paste in a pit, it is almost inevitable that stray materials from the worksite would fall in and become permanently entombed as the artificial stone sets. These are not the signs of a rock that was cut, they are the signs of a rock that was made. The chemical composition adds another layer of undeniable proof. The limestone from the nearby Tura quarries, long believed to be the source for the pyramid's outer casing, has a specific and consistent mineral signature. Yet when scientists performed X-ray analysis on the pyramid stones, they found a startling discrepancy. The pyramid blocks contain minerals, particularly high levels of silicon and other elements, that are completely absent from the Tura bedrock. This is not a matter of a slightly different geological layer. It is a fundamentally different recipe. The evidence points to a manufactured material, a geopolymer where ancient chemists combined crushed limestone with a silica-rich clay and an activator like natron to trigger the chemical reaction that creates new stone. Think of it not as finding a rock, but as finding a baked cake. The ingredients might be from the region, but the final product is a human creation, its structure and composition unmistakably artificial. This is not a fringe idea, it is a conclusion drawn from hard data, from the very atoms that make up the pyramid. The walls of this ancient wonder are not just stone, they are a library, and we are finally learning how to read their chemical text. So how did they do it? What was the actual recipe for this liquid stone? The process begins with a base of disaggregated limestone. This is not about carving big rocks into smaller ones, but about taking soft, naturally occurring limestone and crushing it into a fine powder, almost like flour. This powder, when heated, becomes quicklime, a highly reactive substance that is the fundamental ingredient in all cement, even today. But the ancient chemists did not stop there. The secret ingredient, the true catalyst, was a specific salt called natron. This was not a rare substance. It was harvested from the dry lake beds of Egypt, the same material famously used in the mummification process. Natron is a powerful natural desiccant and alkali, and when mixed with the limestone powder and water, it triggers a violent chemical reaction. It raises the pH level of the mixture dramatically, creating a highly caustic environment. This alkaline soup then begins to dissolve the silica and alumina found in the final crucial component, the water of the Nile River itself. The Nile is not just water, it carries immense amounts of suspended silt, a fine clay rich in the very silicates needed for the reaction. When this silicate-rich Nile water was added to the mix of powdered limestone and natron, a geopolymerization process began. Think of it like baking a cake, where the heat from the chemical reaction itself causes the ingredients to bind and transform into something entirely new. The mixture would become a thick, pourable slurry, a sort of primordial concrete. This slurry could then be carried in baskets, not hauled on sledges, and poured directly into pre-built wooden molds right on the pyramid's rising course. Workers would tamp it down to remove air bubbles, and then, over a period of days, the magic happened. The paste did not just dry out, it underwent a fundamental molecular reorganization. The dissolved silicates from the Nile silt would form new crystalline bonds with the calcium from the limestone, creating a hard, dense matrix that was, for all intents and purposes, a synthetic limestone. The resulting block would be chemically stable, incredibly durable, and perfectly shaped to fit with its neighbors. This was not a primitive method, it was a sophisticated, almost industrial process that leveraged the local environment with genius-level understanding. They were not just stacking rocks, they were brewing stone. This method of casting stone solves the single greatest puzzle of pyramid construction, the ramps. With a liquid slurry, the entire concept of dragging colossal blocks up massive earthen inclines becomes obsolete. A new, far more elegant logistical system emerges, one that perfectly harnesses the Egyptian landscape. The annual flooding of the Nile was not an inconvenience for the builders, it was the very engine of their construction. Imagine a vast network of canals, purpose-dug to channel the life-giving waters of the inundation right to the base of the Giza Plateau. These were not just irrigation ditches, they were the project's industrial arteries. Instead of barges loaded with impossibly heavy, quarried stone picture vessels carrying a different cargo, they are filled with a wet geopolymer mixture, a thick, soupy concoction of crushed limestone, natron, and Nile silt. This liquid stone could be mixed at a central facility and then transported by barge directly to the rising pyramid. The engineering advantage is staggering. Hauling a 70-ton granite block up a steep ramp is a physics-defying nightmare, but lifting buckets of a heavy slurry while still labor-intensive is a problem of human-scale logistics. Workers could hoist these containers using simple counterweight systems and pour the material directly into the wooden formwork on the pyramid's current level. This creates a continuous, upward-moving production line. The formwork acts as a mold, ensuring every block is perfectly sized and shaped as it hardens in place. The joints are seamless because the material was poured against its neighbor, fusing together as it set. This vision transforms the construction site from a chaotic scene of brute force into a highly organized, almost factory-like process. The absence of giant ramps in the archaeological record suddenly makes perfect sense because they were never there. The true ramps were the canals themselves, a fluid highway for a liquid building material, turning the Nile's flood into a deliverer of stone. The visual evidence is right there in the stonework, a story told in two distinct languages. Look at the lower courses of some pyramids, especially the inner core stones. They are rough, irregular, and often have wide gaps filled with rubble and mortar. These are the hallmarks of quarried stone, blocks that were wrested from the earth with immense effort and then painstakingly, imperfectly shaped to fit. Their surfaces are scarred with the marks of tools, and their joints are anything but tight. This is what we would expect from a massive construction project relying on brute force and simple tools. But then, direct your gaze upward to the remaining casing stones, particularly those near the very top of the Great Pyramid. The difference is not just noticeable, it is shocking. These stones are unnaturally smooth, their surfaces almost polished. The joints between them are so impossibly tight that you cannot slide a piece of paper between the blocks. This is a level of precision that seems to defy the very nature of stoneworking with ancient tools. How could the same culture, using the same methods, produce such wildly different results in the same structure? The answer lies in the method of creation. The rough, lower stones fit the traditional story of carving and hauling. They are natural rock and they behave like it. But the perfect, seamless stones above tell a different tale. They are the product of casting. Imagine building a wall not with bricks, but with liquid ceramic that you pour into a mold. Every brick would be an exact duplicate with sharp, clean edges and surfaces as smooth as the mold itself. This is the effect we see in the pyramid's finest work. The ancient builders would have constructed wooden formwork, a perfect negative space of the block they needed to create. They would then pour their geopolymer slurry into this mold right up against the previously cast block. As the material set, it would naturally form a bond, creating that hairline joint. There would be no need for grinding or sanding, no risk of a chisel slipping and ruining a surface. The mold guaranteed the perfection. This two-tiered approach makes perfect strategic sense. The builders used quicker, rougher methods for the vast internal core, the part that would never be seen. But for the magnificent outer skin, the pyramid's public face that would gleam in the sun, they deployed their most advanced technology. They switched from carving rock to growing it in place, achieving a perfection that has stood as a silent, mocking challenge to conventional history for thousands of years. The pyramid itself is the proof, its two contrasting styles a permanent record of a technological shift hidden in plain sight. This glaring absence of evidence forms a silent but powerful argument of its own. If the traditional narrative is correct, the landscape around Giza should be an industrial wasteland of epic proportions. The Great Pyramid alone is estimated to contain around 2.3 million limestone blocks. Each of these blocks had to be cut from a solid bedrock quarry. The scale of this operation would have left behind a scar on the earth so massive it would be visible for millennia. Yet when we look at the known quarries, the math simply does not add up. The quarries we have identified, like the one at Tura, are not large enough to account for the sheer volume of stone. It is like trying to explain a mountain of gravel by pointing to a small sandbox. The missing stone amounts to millions of cubic meters of material that has simply vanished from the geological record. Where did it all go? More importantly, consider the debris from the carving process. Cutting that many blocks from solid rock does not just remove stone, it creates an immense amount of waste. The process of splitting and shaping each block would have generated a mountain of chips, dust, and broken fragments, a volume nearly equal to the pyramid itself. This debris does not biodegrade, it is permanent. So where is this colossal pile of rubble? It is not surrounding the Giza plateau. There is no equivalent mound of limestone chips matching the pyramid's own mass. This is not a minor oversight, it is a catastrophic hole in the traditional story. The tools present another baffling silence. Quarrying on this scale with copper chisels and stone hammers would have required an almost infinite supply of these implements. Copper is a soft metal, and chisels used to cut hard limestone would have dulled after just a few strikes. The quarries should be littered with countless broken and discarded bronze tools, a veritable graveyard of failed equipment. Yet such a deposit has never been found. The handful of tools discovered by archaeologists could not possibly account for the construction of the greatest stone building on Earth. The evidence that should be everywhere, the mountains of waste, the endless tool fragments, the quarries large enough to hold entire mountains, is conspicuously, undeniably absent. This void speaks volumes, pointing away from a story of brute force carving and toward a far more sophisticated and far cleaner method of creation. The proof of any theory lies in its recreation. Can we, with our modern understanding, replicate the ancient magic of liquid stone? This is the domain of experimental archaeology, where scientists step into the shoes of the pyramid builders to test the geopolymer hypothesis with their own hands. One of the foremost pioneers in this field is the French materials scientist Joseph Davidovits. For decades, he has championed the idea of an ancient concrete, and he has put his theory to the ultimate test, the furnace. In his laboratory, Davidovits and his team have recreated the proposed ancient process on a small but definitive scale. They begin by gathering the very ingredients the Egyptians would have used: a fine powder of common limestone, a source of silica-rich clay, and the crucial catalyst natron salt. These are mixed with water to create a thick gray slurry, a mixture that looks unremarkable like wet cement. This paste is then packed into wooden molds, simple boxes that represent the formwork used on the Giza Plateau. The real transformation begins with heat. The molds are heated gently, mirroring the warm Egyptian sun, which accelerates the chemical reaction. Over a period of days, the geosynthesis occurs. The mixture does not simply dry, it undergoes a fundamental molecular change. The alkaline natron dissolves the silica from the clay, allowing it to form new, strong bonds with the calcium in the limestone powder. The result is a solid, hard block of synthetic stone. When these laboratory-made blocks are analyzed, the data is startling. X-ray diffraction tests reveal a chemical signature that is a near-perfect match for samples taken from the Great Pyramid's own casing stones. Both contain the same unique mix of minerals and the same telltale amorphous structures, a fingerprint of a created geopolymer, not a naturally formed crystalline rock. The laboratory blocks even exhibit the same microscopic features, the trapped air bubbles and occasional organic fibers that are found deep within the pyramid's heart. This is not a vague similarity, it is a chemical echo across 4,500 years. These small-scale experiments prove that the process is not only possible but plausible. They demonstrate that the ancient Egyptians possessed all the necessary materials, and with a spark of genius, the knowledge to combine them into one of history's most enduring building materials. The stone of the pyramids was not just found, it was forged. For decades, this theory was relegated to the absolute fringe, dismissed as little more than pseudo-scientific fantasy. The Egyptology establishment met the geopolymer hypothesis with a wall of firm resistance. It challenged not just a single fact, but the entire foundation of their field, the very story of how ancient civilization operated. To accept it was to admit that a core chapter of human history might be completely wrong. But a revolution rarely starts in the center, it begins at the edges. The first to take notice were not archaeologists, but geologists and materials scientists. These were professionals who spent their lives not interpreting texts but reading the language of rocks. When they looked at the microscopic evidence, the air bubbles and the strange mineral compositions, they saw something the archaeologists could not: the undeniable signature of a chemical process. The data was objective, and it was pointing overwhelmingly toward a synthetic origin. One by one, respected figures in the hard sciences began to publicly endorse the idea, bringing a new credibility to the debate. The theory began its slow, arduous climb from the fringe into the realm of legitimate scientific inquiry. Today, the division is stark. On one side, you have the vast majority of archaeologists, guardians of a traditional narrative built over a century. On the other, a growing coalition of chemists, geologists, and engineers, armed with electron microscopes and X-ray diffractometers, presenting evidence that is increasingly difficult to refute. This is not a conflict of personalities, but a fundamental clash of methodologies, a battle between the interpretation of artifacts and the analysis of atoms. This growing acceptance makes the idea all the more thrilling because it mirrors every great scientific upheaval in history. The notion that the Earth revolves around the Sun was once a laughingstock. The theory of plate tectonics was initially considered absurd. Every paradigm shift begins with an idea that seems at first impossible. The geopolymer theory is now in that volatile, exciting phase where each new piece of evidence chips away at the old certainty, forcing us to question everything we thought we knew about the dawn of engineering. Perhaps the most compelling evidence for this lost chemical art lies not in a stone, but in a man. Centuries before the Great Pyramid rose from the sands, another genius walked the earth, a figure so brilliant he was later worshipped as a god. His name was Imhotep, the legendary architect of the first pyramid ever built, the Step Pyramid of Djoser. History remembers him as the world's first architect, a master builder. But what if his true title has been misunderstood for millennia? What if Imhotep was not just an architect, but the world's first great chemist? He was deified by the Egyptians as a god of wisdom and medicine, a patron of healing and knowledge. This is a crucial detail. Medicine in the ancient world was a profound science of compounds and tinctures, a deep understanding of how substances from the earth could transform the human body. Imhotep would have known the reactive power of natron from the mummification process. He would have understood how different clays and minerals behaved when mixed and heated. His genius was likely a fusion of these disciplines. He did not see a boundary between healing the body and shaping the world. The same knowledge that allowed him to create poultices and medicines could have been applied on a colossal scale to create a new kind of stone. The Step Pyramid was his prototype, the world's first large-scale experiment in geopolymer chemistry. It was a revolutionary leap from building with mud brick to creating artificial limestone, a technology that would then be refined and perfected by his successors at Giza. This connection transforms the theory from an abstract idea into a human story. It gives a name and a face to this lost science. Imhotep becomes the archetype of the ancient scientist, a man whose understanding of the molecular world was so advanced it allowed him to literally grow mountains. His deification makes perfect sense. To a people who watched him perform what seemed like magic, turning dust into enduring stone, he was not just a man. He was a master of the very elements, a true god of wisdom. The echoes of this lost science are not confined to the sands of Egypt. If the geopolymer theory holds water for the pyramids, then we must turn our gaze to other ancient marvels that have long baffled archaeologists with their impossible stonework. Consider the ruins of Pumapunku in Bolivia, a site that feels less like a ruin and more like a celestial factory floor. Here, the stonework is so precise it defies logical explanation. Massive blocks of andesite, a stone harder than granite, are cut with razor-sharp, perfectly straight grooves and drilled with holes of impossible uniformity. The surfaces are so smooth they appear polished by machines, and the complex interlocking shapes fit together with a geometric perfection that seems to deny the use of simple hand tools. The conventional explanation of hammerstones and patient abrasion feels woefully inadequate. It is as if the stones were not carved but molded and cast into these intricate forms, much like the perfect casing stones of the Great Pyramid. This is not a coincidence, it is a pattern. Across the globe, the Romans achieved a similar feat of material science with their legendary concrete. Structures like the Pantheon, with its vast, unsupported dome, have stood for 2,000 years, resisting earthquakes and the slow decay that crumbles modern concrete. The secret to Roman concrete's longevity has only recently been uncovered by scientists. The Romans mixed lime and volcanic ash, a reactive silica-rich material, with seawater. This created a chemical reaction that formed incredibly stable mineral crystals, a geosynthesis eerily similar to the proposed Egyptian process. Their concrete was not just a mixture, it was a living rock that grew stronger over time, healing its own cracks as crystals continued to form. The Romans were not carving stone, they were growing it, mastering a chemistry that we are only now beginning to reverse engineer. These scattered examples from different continents and cultures point toward a startling possibility. This was not an isolated spark of genius in one river valley. It suggests a deeper, more widespread understanding of geopolymer chemistry in the ancient world, a knowledge of how to manipulate earth and fire and water to create new forms of stone. This was a global, yet apparently disconnected, material science. Each culture, from the Egyptians to the Tiwanaku of South America to the Romans, may have independently discovered the fundamental principles of activating silica and alumina with alkalis to bind stone. They used the materials they had on hand: Egyptian natron and Nile silt, Bolivian volcanic rock, Italian volcanic ash and seawater, but the underlying chemical logic was the same. This points to a profound, recurring human ingenuity, a lost chapter in our history where the line between alchemy and engineering was blurred. The true mystery is not just how they built these structures, but why this profound knowledge of synthetic stone was lost, fading from memory, and leaving behind only these silent, magnificent puzzles for us to decipher. This very same stone holds the key to another long-standing puzzle, the mystery of the tool marks. Egyptologists have long pointed to certain striations and grooves on pyramid stones as definitive proof of quarrying with copper chisels. But what if we have been misreading these ancient inscriptions all along? Under the geopolymer theory, these marks are not from carving but from casting. They are the ghostly impressions of the wooden formwork and the tools used to handle the wet, synthetic stone. Imagine the process. Workers would have constructed sturdy wooden molds to contain the thick slurry. As the geopolymer mixture was poured and tamped down, it would have picked up the texture of the wood grain itself, leaving behind fine, parallel lines that we now mistake for the repetitive strikes of a chisel. Deeper grooves could be the marks of the wooden tools used to mix and pour the heavy substance, or even the seams where different sections of the formwork were joined together. This recontextualization turns the old evidence on its head. The marks are not a record of subtraction, of stone being painfully removed, but of addition, of stone being formed. It explains why these marks sometimes appear in patterns that seem illogical for quarrying, or on surfaces that would have been hidden from view. A worker carving a block would focus on the visible faces, but a worker pouring liquid stone would leave marks on every surface that touched the mold, even the bottom. This single shift in perspective demonstrates the immense explanatory power of the new theory. It does not dismiss the evidence, it simply reads it in a different language, one that tells a far more sophisticated story of creation, where the very tools of the builders left their signature not through force, but through contact preserved for millennia in a stone that was once fluid. This new method of construction completely rewrites the social and economic story of the pyramids. Forget the popular image of hundreds of thousands of slaves straining under the lash, a sea of humanity driven by cruelty. The geopolymer theory presents a radically different picture, one of a highly organized, technologically advanced society. Pouring liquid stone would not require a massive army of unskilled laborers. It would demand a much smaller, highly specialized workforce of chemists, technicians, and engineers. Imagine the project not as a public works program for idle farmers, but as a sophisticated, state-run chemical operation. The brute force of dragging stones is replaced by the intellectual force of mixing them. Instead of overseers with whips, you would have foremen with precise recipes, men who understood the delicate balance of natron, limestone powder, and Nile silt. These were the ancient equivalents of master brewers or material scientists, carefully managing a chemical reaction on an industrial scale. The workforce shifts from tens of thousands of laborers to perhaps a few thousand skilled artisans and their assistants. The primary labor would involve gathering and crushing limestone, mixing the slurry in large vats, and then carrying the heavy but manageable buckets to the rising pyramid course. This is back-breaking work, to be sure, but it is work of a different kind, work that is organized, repeatable, and scalable. It relies on knowledge and process, not just on immense numbers and muscle. This vision transforms ancient Egypt from a society capable of immense coercion to one capable of profound innovation, a civilization that valued specialized knowledge as much as raw manpower. The true monument at Giza is not just to a pharaoh's power, but to the quiet genius of its forgotten chemists. This very chemistry creates a fascinating puzzle for modern science, one that has likely sent researchers down the wrong path for decades. Carbon dating, our gold standard for determining the age of ancient organic materials, faces a unique challenge when applied to the pyramids. The method works by measuring the decay of radioactive carbon-14 in a sample, a clock that starts ticking when a plant or animal dies. For a piece of wood or charcoal found in a pyramid, this is straightforward. But what happens when we try to date the stone itself? If the geopolymer theory is correct, the pyramid blocks are made from crushed limestone, a sedimentary rock formed from the skeletons of ancient marine creatures. These creatures lived and died millions of years before the first pharaoh ever ruled Egypt. When the builders gathered this ancient limestone and crushed it into powder, they were essentially recycling primordial life. Any carbon dating performed on the stone would therefore capture the age of the original marine organisms, not the moment the block was cast. The test would return a date of thousands or even millions of years before the pyramid was built, a result that seems to shatter the established timeline. This is not a flaw in carbon dating, it is a misinterpretation of what the sample actually represents. For generations, such confusingly ancient dates may have been quietly dismissed as contamination or error, when in reality they were a direct clue to the synthetic nature of the stone, a signal we failed to decode. The stone was not lying, we just did not know how to listen. It was telling us its raw material age, not its construction date, a vital distinction that resolves a long-standing scientific conundrum and turns a supposed counter-argument into a powerful piece of supporting evidence. Perhaps the most visually stunning proof of this theory lies in the legendary casing stones. We have all seen the familiar image of the Great Pyramid as a rough, stepped mountain of brown blocks. But that is not how it was originally built. In its prime, the pyramid was encased in a brilliant white shell of polished Chora limestone, stones so perfectly fitted and so flawlessly smooth that the entire structure was said to gleam like a mirror under the Egyptian sun. Most of these stones were stripped away over the centuries to build the mosques and palaces of Cairo, but a precious few remain, clinging stubbornly to the very base of the structure. And these survivors tell a remarkable story. Their surfaces are not merely flat, they are optically flat, with a polish so fine it feels almost like glass to the touch. Now think about the process of achieving this finish on a natural stone block. You start with a colossal, multi-ton block of hard limestone, fresh from the quarry, its surface rough and irregular. Craftsmen would have to labor for weeks, maybe months, with abrasive sand and water, painstakingly grinding down the entire face by hand to achieve that legendary smoothness. It is an almost unimaginable feat of endurance and precision, a task so difficult it borders on the absurd when you consider the scale, with tens of thousands of casing stones requiring the same impossible treatment. But what if that smoothness was not carved into the stone but cast from the very beginning? The process changes entirely. Instead of starting with a rough, uneven surface, the ancient workers would have poured their geopolymer slurry into a mold made of the smoothest wood or stone they could produce. The resulting block would harden with a surface that was already incredibly flat and uniform, a perfect impression of the mold itself. The final polishing would then be a relatively simple task, a matter of buffing an already near-perfect surface to a high sheen, rather than grinding down a mountain of rock. This is not just a different method, it is a different world of possibility. The legendary smoothness of the pyramids was not an achievement of endless manual labor, but a natural byproduct of a brilliant manufacturing process. The few remaining casing stones are not just ancient relics, they are the clearest, smoothest evidence we have that the pyramid builders were not just moving mountains, they were sculpting them from liquid. Of course, any theory this revolutionary faces fierce and understandable skepticism. To be fair, mainstream Egyptology presents several powerful counter-arguments that cannot be ignored. The first and perhaps most compelling is the discovery of quarry marks found directly on some of the pyramid's core blocks. These are painted hieroglyphs, names of work crews like the Friends of Khufu gang, that appear in the hidden inner chambers. Critics ask a very logical question. If these blocks were cast in place from a liquid slurry, how did these painted marks get there? You cannot paint a tidy hieroglyph on wet concrete and expect it to stay. It seems to imply the blocks were already finished, labeled, and then hauled into position, just as the traditional story suggests. Then there is the undeniable evidence of the pyramid's internal architecture. The massive granite beams that form the roof of the king's chamber are a perfect example. These are not simple blocks, they are colossal, 70-ton lintels of solid granite, a stone so hard that creating a synthetic version seems implausible even with this theory. Their sheer weight and the way they are engineered to distribute stress point directly to them being quarried and shaped, not poured. This suggests the builders used both methods, perhaps casting the limestone shell while still relying on quarried stone for critical structural elements. But the most haunting question from skeptics is one of silence. If this chemical knowledge was so advanced and so central to building the greatest structures on Earth, why is there not a single written record, not one papyrus or inscription, that details the recipe for liquid stone? We have administrative texts listing quantities of bread and beer for workers. We have religious hymns, we have medical manuals, but we have no cookbook for concrete. This absence is deafening. It seems inconceivable that a civilization so meticulous in its record-keeping would allow its greatest technological secret to vanish without a trace, leaving behind not a single written clue. These are not minor objections, they are the pillars of the traditional view, and any new theory must find a way to answer them convincingly. These objections are powerful, but the geopolymer theory offers compelling answers that turn these very points into pillars of its own argument. First, the quarry marks. It seems logical that a painted mark means a block was quarried. But what if the mark was painted not on the finished block, but on the wooden formwork itself? Imagine a worker using a brush to label a mold, identifying which crew was responsible for that particular pour. When the liquid stone slurry was poured into that marked mold, the wet material would have absorbed the pigment from the paint, transferring the hieroglyphic inscription directly into the very surface of the stone as it hardened. The mark would not be sitting on top, it would be fused within the top layer of the block, a ghostly imprint from the mold. Alternatively, these marks could have been placed on the foundational layer of stones, the actual quarried blocks that formed the base of the pyramid, to guide the construction of the cast layers above. This would explain their presence without contradicting the primary use of synthetic stone for the immense volume of the structure. Then we face the granite beams in the king's chamber, a formidable challenge. The theory does not need to claim that every single element was cast. It is entirely plausible, even logical, that the builders used their most advanced method for the bulk of the work, the limestone shell, while still relying on traditional, heroic quarrying for specific, critical components that required the unique properties of solid granite. This was not an all-or-nothing technology, it was a flexible toolkit. The most profound rebuttal, however, addresses the deafening silence in the written record. Why is there no recipe for the most important building material in their history? The answer may lie in the sacred nature of this knowledge. This was not a mundane craft like pottery or weaving. It was the secret of creating stone itself, a power that transformed dust into a monument for a god-king. Such a potent formula would have been protected as a state secret, a sacred mystery known only to a small, initiated priesthood of master builders, perhaps even a secret passed down orally from Imhotep himself. Writing it down would have been unthinkable, like publishing the nuclear codes. Its value was in its exclusivity. This knowledge was not lost through carelessness, but was deliberately guarded, and when that priestly lineage was eventually broken, the secret died with them. The absence of a written record is not a hole in the theory. It is the signature of a secret so powerful it was never meant to be written. This ancient chemical process reveals an unexpected layer of sophistication, one that positions the pyramid builders as pioneers of sustainable architecture. The traditional method of quarrying and hauling stone is an inherently brutal affair for the landscape. Imagine the scars left behind, entire mountainsides carved away, vast amounts of rubble and dust generated for every single usable block. The environmental footprint would have been colossal, a permanent wound on the earth. The geopolymer method, by contrast, is remarkably clean and efficient. It leverages materials that are locally abundant and low impact. The primary ingredient was simply soft, naturally disaggregated limestone, which could be gathered and crushed far more easily than cutting monolithic blocks from a quarry face. This process creates powder, not massive waste chips. The other key components, the natron salt and the silt-laden water of the Nile, were readily available natural resources. This system was a closed loop of local sustainability. Instead of causing irreversible damage to distant quarries and clogging the landscape with unusable debris, the builders utilized what was immediately at hand. The only real byproduct of the casting process would have been the wooden formwork, which could be reused again and again. This paints a profoundly different picture of ancient resource management. It suggests a civilization that was not only technologically brilliant but also deeply resource-conscious, understanding how to achieve monumental goals without laying waste to their environment. They were not conquerors of nature, but collaborators with it, using chemistry to transform the very dust beneath their feet into a monument for eternity. This silent, efficient process stands as a timeless lesson in building not just for grandeur, but for harmony with the world. The original geopolymer proposal from the 1980s was a bold starting point, a radical idea that challenged everything. But science does not stand still, and neither has this theory. It has evolved, refined by decades of new research and cutting-edge technology that allows us to peer inside the stone without ever lifting a chisel. Recent international scanning projects like the landmark Scan Pyramids mission are using cosmic rays and thermal imaging to see through the ancient masonry. These are not speculative guesses, they are data-driven investigations, and what they are finding continues to baffle traditional explanations. The scans have revealed large, unexplained voids within the Great Pyramid, empty spaces that do not align with any known corridors or chambers. More intriguing are the thermal anomalies, spots where the stone cools at a different rate than the surrounding blocks, suggesting a fundamental difference in density or composition. Why would some blocks be different if they were all quarried from the same uniform bedrock? This inconsistency is a quiet alarm bell. Another study used advanced microscopy to analyze the mineral makeup of the pyramid stones, discovering a highly amorphous, non-crystalline structure in many samples. Natural limestone is a crystalline rock, its atoms arranged in a tight, repeating pattern. The pyramid stone, however, shows a disorganized, glass-like structure, the exact fingerprint of a rapid chemical setting process, not a slow geological formation. These are not the findings of fringe researchers, they are the results published in peer-reviewed scientific journals. The anomalies are real and they are persistent. Each new scan, each new analysis adds another layer of complexity that the simple story of ramps and ropes struggles to accommodate. The theory is no longer a static idea from the past. It is a dynamic, living framework that is continually tested and surprisingly often confirmed by the very stones it seeks to explain. The implications of this discovery ripple far beyond the sands of Giza, forcing a profound re-evaluation of ancient ingenuity across the globe. If the Egyptians possessed a sophisticated science of synthetic stone, then we must look at other legendary monuments with a new and questioning eye. The narrative of human history, which often paints a linear progression from primitive to advanced, begins to crack and crumble. This is not just about solving one architectural puzzle, it is about confronting the possibility of a forgotten technological epoch. What other so-called miracles of the ancient world were not miracles at all, but the products of a lost material science? The massive stone walls of Sacsayhuaman in Peru, where colossal blocks fit together in a complex, jigsaw-like pattern with such precision that not a blade of grass can grow between them, have always been explained by generations of patient labor with stone tools. But the geopolymer lens offers a different vision. What if these intricate, multi-angled stones were not painstakingly ground into shape over centuries, but were molded into their perfect, interlocking forms, poured into custom-made formwork that guaranteed a seamless fit? The sheer logistical nightmare of carving and moving these behemoths vanishes, replaced by the elegant, chemical solution of creating them in place. This same logic could apply to the mysterious stone jars of the Plain of Jars in Laos, thousands of massive stone vessels scattered across the landscape. Their origin has baffled archaeologists for decades. How were they carved from solid rock and transported? The answer might be that they were not transported at all. They could have been cast directly on site, their forms emerging from the earth itself through a chemical process we are only now relearning. Even the colossal stone heads of Easter Island, the Moai, stand as silent sentinels to a mystery. The official story involves carving them with stone picks and then somehow walking them miles across the island. But what if the process was far more direct? What if the islanders discovered a local volcanic rock that could be disaggregated, mixed with a binder, and sculpted into these immense figures, reducing a feat of superhuman logistics to a manageable act of communal creation? This new perspective does not diminish these cultures, it elevates them. It suggests that scattered across time and continent, human civilizations repeatedly stumbled upon the fundamental principles of geopolymer chemistry, using the materials they had to manipulate their world in ways we deemed impossible. Our history books have often interpreted the absence of advanced metal tools as proof of simple methods, but we may have been looking for the wrong kind of technology entirely, missing the quiet, chemical genius that turned Earth into enduring art. This is the true paradigm shift. It forces us to stop asking how they carved these stones and start asking a far more thrilling question: what else did they know that we have forgotten? Yet for all its compelling evidence, the geopolymer theory remains a magnificent puzzle with pieces still missing from the box. The precise chemical catalyst that triggered the reaction so reliably remains one of the biggest enigmas. Was it truly just natron and Nile silt, or was there another, more potent ingredient, a secret activator that has eluded modern recreation? We can create small, convincing blocks in a lab, but the ancient Egyptians managed this on an almost incomprehensible industrial scale, producing millions of identical blocks with unwavering quality. How did they achieve such flawless consistency across decades of construction, batch after colossal batch, without modern quality control? It speaks to a level of process engineering we rarely attribute to the ancient world. And then there are the physical remnants of this great chemical kitchen. Where are the massive mixing pits that would have been needed to churn such vast quantities of slurry? Where are the specialized vats, the unique tools for handling the corrosive paste, the centralized production facilities that must have dotted the Giza Plateau? These industrial sites have not been found, leaving a glaring hole in the archaeological landscape. These are not minor gaps, they are fundamental questions that keep the mystery vibrantly alive. This is not a case closed, but an active, thrilling frontier of science. Every unanswered question is a beacon, guiding a new generation of chemists, archaeologists, and engineers in a hunt that is far from over. The stones have given up some of their secrets, but they are still whispering, challenging us to uncover the final, lost chapters of their creation. This is the heart of the dilemma that leaves experts so unsettled. For over a century, the entire field of Egyptology has been built upon a specific narrative of human progress, one that moves in a straight, predictable line from simple to complex. We have meticulously documented the evolution of tools from stone to copper to bronze to iron, and we have mapped the rise of empires through their artifacts and texts. The pyramid, in this view, was the ultimate achievement of a Bronze Age society, a triumph of sheer human will and organizational skill. It was impressive, but it fit neatly into our timeline. The geopolymer theory shatters that timeline. It does not simply add a new chapter, it demands we rip out the old one and replace it with something far more revolutionary. It proposes that a civilization we thought we understood possessed a branch of material science so advanced it parallels discoveries we made in the 19th and 20th centuries. We point to the invention of modern Portland cement as a hallmark of our industrial ingenuity, yet this theory suggests the Egyptians were mastering a similar, perhaps even superior, chemical process 4,500 years earlier. This is not a minor adjustment, it is a full-scale paradigm shift. It forces our uncomfortable but thrilling admission that human history is not a steady, upward climb, but a story of peaks and valleys, of brilliant knowledge that flares into existence and then vanishes for millennia. The pyramid is no longer just a tomb, it is a fossilized piece of advanced technology, a permanent question mark etched into the landscape, challenging everything we thought we knew about the journey of innovation. So we stand at a crossroads between two ancient worlds. One is a story of ramps and ropes, a tale of immense human effort we have told for generations. The other is a vision of liquid stone and chemical mastery, a revolutionary idea that redefines ingenuity itself. While this cast stone theory is not yet proven beyond all doubt, it offers something profoundly valuable, compelling answers to the very puzzles that have baffled experts for centuries. It explains the missing quarries, the impossible precision, and the ghostly tool marks. It transforms the construction site from a scene of brute force into a sophisticated chemical laboratory. The old narrative is comfortable, but it is filled with gaps. The new theory is radical, but it fits the evidence in a way that feels almost inevitable. The pyramids have guarded their secrets for millennia, but with new science and new ideas, we might finally be on the verge of understanding how they truly came to be. What do you think? Could the pyramids be made of poured stone? Let us know your thoughts in the comments below, and don't forget to subscribe for more mysteries of the ancient world.